What can one poor maintenance decision cost you? Or a single bad adjustment? Or just one wrong part number? When it comes to brake balance, the answer is a lot, in both safety and budget dollars. Unbalanced brakes can provide unpredictable stopping power in critical situations, increase jackknife potential, and damage or destroy drums, blocks, and other brake system components. In addition, they can cause thousands of dollars in unnecessary downtime. In the last 2 decades, the need for good brake balance has increased substantially. Factors like streamlining and reduction of drivetrain drag for fuel efficiency have drastically decreased a rig's natural rolling resistance. So the brakes have to work harder to stop the vehicle. During a 6-year period back in the 1970s, for example, the braking power needed on a 3% grade increased 369%, and that trend continues. That's why proper braking at each wheel and correct tractor-to-trailer timing is so much more important in the 1990s. Ideally, each wheel on a single or tandem axle should provide equal braking power, and the percentage of braking done by the tractor and the trailer should equal the portion of weight each carries. For example, a tractor carrying 57% of the total vehicle weight should typically provide approximately 57% of the total braking power. Achieving that kind of good proportioned braking demands 3 kinds of balance: air or pneumatic balance, torque balance, and mechanical balance. All are interrelated. Pneumatic balance is meaningless if the mechanical and torque systems are not also balanced. And mechanical and torque balance cannot be undertaken until pneumatic balance is achieved. This video will cover all 3 types of balance, beginning with pneumatic. From the compressor to the wheels, a pneumatic system consists of a complex network of valves, tanks, and tubing. Obstructions and dirt in the system can radically affect the air pressure delivered to the brake chambers. So even on vehicles equipped with dryers, air tanks should be drained overnight at every preventive maintenance inspection. And tanks on vehicles without dryers should be drained daily. The types of fittings and size of tubing used in a system are also crucial. Drilled brass 90-degree elbows, for example, reduce the airflow rate. And replacement lines of different lengths or diameters alter air speed as well. So lines and fittings should always be replaced with identical sizes and types. The model of valve used can also affect balance. The primary differences in valves are their crack pressures and differentials. Crack pressure indicates the initial air pressure required in a control line to activate a valve. For example, a relay valve that requires 4 psi to open is said to have a 4 psi crack pressure. Once opened, the difference between the control line pressure and delivery pressure is the differential. For example, a valve that receives 10 psi of control air may deliver only 8 psi of supply air to the brake chambers. The 2 psi difference is called the valve differential. Using a replacement valve with either a higher or lower crack pressure and differential can dramatically affect brake balance, as this simplified example demonstrates. With 20 psi application pressure, substituting a valve with a 4 psi differential for a valve with a 10 psi differential decreases the differential by 6 psi and increases the air supplied to all affected wheel chambers by the same amount. This radically changes the brake balance. It's easy to make incorrect replacements because the valves and valving systems used by the top dozen tractor manufacturers are far from identical, and they frequently change from model year to model year. In addition, standard replacement valves frequently have much different crack pressures at differentials than original equipment valves. For example, in the early 1980s, some new systems were introduced that utilized the primary circuit for one tandem axle and the secondary circuit for the other tandem. Traditionally, most systems use the primary circuit to supply the tandem axles and the secondary circuit to supply the steer axle. In addition to this design change, some of the split systems introduced quick-release valves with crack pressures as high as 20 psi. But most standard replacement quick-release valves have differentials of just 0 to 1 psi. And the relay valves used on split systems have crack and differential pressures as high as 10 psi. but standard replacements have differentials of only 3 to 4 psi. Identifying the right replacement valve can be difficult because valves that look identical can have cracked springs of different strengths or no springs at all. As a result, their crack pressures and differentials can be far different. The only way to assure exact replacement is to exactly match the OEM part number. But on remanufactured valves, even the part numbers stamped on the housing are not reliable. So it's important to always check the actual part number on the attached tag. Recent efforts to standardize valve identification promise to eliminate valve replacement confusion. New guidelines developed by the Society of Automotive Engineers and the Maintenance Council of the American Trucking Association use 5-digit codes to identify the valve type and nominal crack pressure. The codes are inscribed on corrosion-resistant tags or labels designed to remain legible and securely attached. In this example, the first 2 letters, RV, indicate that the part is a relay valve. The following 3 digits, 105, indicate a 10.5 crack pressure. Here, BV075 identifies the device as a brake valve requiring 7.5 of nominal crack pressure. Serious balance problems normally show up in irregular braking or block wear. However, indications of minor balance problems may be far less obvious. While fleets can use gauges to check valve differentials against original equipment specifications, it's a time-consuming process. And some OE tractor systems may not be compatible with some trailer systems. So there's no guarantee that factory specifications will yield balanced